Hi there, welcome back. In the last episode, we destroyed this building. Later, we'll simulate the splashes from the collision between this building and the tsunami, so we need it to be polygons. As you can see, it is a packed object now, so let's unpack it. Then cache it for a faster running. The frame range is 1 to 150. Time shift has been set properly. Alright, done with the destruction of this building. Let's move on to another one. There's not much difference in the fracturing process, so I'll just go through it briefly. At first, separate the individual parts and merge objects that are of the same type. Then delete all elements that cannot be seen in the camera. You can delete something like the glass and window frames, but don't delete anything of the building's main structure, like the floors and walls inside it, because they support the framework. The next step is to fracture these parts. Here I scattered some regular points, then multiplied them, and made a random distribution. As to the glass fracture, I used RBD material fracture. There is a glass type available, which gives our broken glass a more realistic look. These parameters can be adjusted as per your needs to achieve your desired effects. These pillars are of different shapes and sizes. If we simply apply a for loop, the sizes of the shattered pieces will differ greatly. So we'd better classify them. Here I classify them according to their shapes. The above pillars are long and thin, while the below ones are short and thick. Let me explain it in detail. Say we've got a relatively flat object, measure its volume and its area. Convert these attributes from primitive class to detail, and then we get a sum of its area and volume. Keeping the same area, create a sphere which has the largest volume in all shapes. Now keep the same volume, create another sphere. It looks much smaller than the previous one. Let's make the flat object thinner. Then its area is just a bit smaller, whereas its volume is much smaller. See how the spheres change. This sphere has the same surface area with the flat object, and this one has the same volume. Obviously, their radii are different. You may have noticed when I change the scale on the y-axis, the ratio of the radii of these two spheres changes accordingly. The flatter the object, the greater the difference between the sphere's radii. Say the object is not flat but a cube. Then the sphere of the same area turns out to be like this. And the sphere of the same volume ends up like this. It can be seen that their radii are almost the same. Let's make it a sphere. Now these two spheres are of the same radius. That is, the ratio of their radii is 1. Briefly, the ratio of the radii of these two spheres reflects how flat the object is. Here are the formulas for calculating the volume and area of a sphere. Because Houdini has worked out the volume and area, we only need the ratio of the radii to know how flat the object is. So let's calculate the radii. Okay, this is how to get the radius of a sphere by a given volume. If we transfer it to an expression in Houdini, it's like this. Note that it's 1.0/3 rather than 1/3. If you omit 0.0, the result will be an integer, 0, which is wrong. Of course, you can also calculate the radius by a given area. With the above explanation, I believe you can understand the expressions here. This is how to find the ratio of the two radii, but it's currently in the detail class. Since the ratio of the radii is calculated in the primitive class, we need to convert the area and volume from detail to primitive. Set promotion mode back to its default. Here is the ratio. Let's lower the value on the y-axis. See, the flatter the object, the larger the ratio is. So we can use the ratio to determine the object's flatness. Say there are many objects and you want to calculate them together, then you'll need a for each for this process. But here it's being converted to detail, so all objects will be processed as a whole, and the result will be wrong. Here I used another way. I didn't use attribute promote, but calculated the ratios directly in the primitive class. Create the name attribute for each connected piece. Then measure the volume and the area for each piece. Put expressions here as explained above. If it is a bit complicated for you, you may try group these pillars as per their areas. Add a connectivity node. Then measure the area of each connected piece. This way we can split it to different types of pillars based on their areas. So all rows lead row. Then cache out the fractured pieces. The following two steps are the same as we did before. Next, referring to the structure of real buildings, merge the adjacent parts. Then create constraints. Here we merged the glasses and window frames. Merge 15 here is a combination of all building parts except the glass. Then add an RBD cluster, which is used to generate the cluster attribute. You can color the building to highlight the clusters. The pieces in the same color will fall apart as a whole. And here you can adjust the size of each cluster and scale up detach ratio to add some small pieces. But I prefer the distribution of clusters like this. Then scatter some points. Note, the cluster attribute should be inherited by this node. And then transferred to these packed objects. Then unpack them, for we will create constraints later. Still keep the cluster attribute. Then convert the cluster attribute from point class to primitive class. Create constraints for one cluster. And use for each to loop through all clusters, so that the constraints of the whole building will be done in clusters. That is, the pieces in the same color are connected as a whole. When we break the building, it will fall apart easily from the seams. This distribution of the clusters is exactly what we want. Suppose the foundation of the building is pretty strong, then the upper part will lean forward when the building is hit. So here I create a group for the bottom, making it a passive object. Here I animate an object to have it collide with the building. It's very simple. Get into dot. Import the building, ground, and the object that hits the building, and import the corresponding constraints. Here we have two glue constraints and one soft constraint. For the soft one, I set the angle limit to break the constraints. I have made a flipbook. You may find the building falling on the ground unnaturally, but fortunately, we only need the beginning part of this animation, because we cannot see the ground as the tsunami covers the building. So just pay more attention to the visible part. Actually, it's good enough to do the job. We can see here how the building falls apart in clusters, which totally follows the colored distribution. Here is the animation with the glass. These settings are basically the same as we did in the last episode. Then shift time to match the dynamics of the glass with that of the tsunami. I lower the speed here, cause the dynamics at the beginning are a bit too fierce. The dynamics are disabled at first, and at the 60th frame, enable the dynamics. In the 125th and later frames, the building will be flooded by the tsunami, so we set frame here to 125 to prevent the building from disappearing. So much for the destruction of this building. The destruction of other buildings is done in the same way, so I'll skip it. This is a background building. Most of it is blocked from view by the front buildings, so I used a simple way to break it. This background building is not a standard model, so it's hard to classify all different elements. Here I just divided them into three groups: the inner structures, the outer walls, and the glass. I roughly fractured the outer walls. As you can see, there are not many pieces. Then I merged them with the inner structures. I didn't shatter the inner structures, mainly because they're complicated and it's hard to group the different elements in detail. So I cannot follow the normal workflow. First, obtain the bounding box of the building and subdivide it. Add a mountain and create a deforming motion through keyframing. Then drop transform and animate the box by adjusting translate and rotate here. At last, use point deform to transfer the deformation to the building. Connect the first port here with the building, link the second one to the proxy geometry, and plug the animated deformed proxy into the last port. Make sure the polygon counts of the second and third input are the same, so that the data of deformation can be transferred correctly. We can adjust the building's deformation by making settings to mountain here. And this transform animates the building to lean backward and sink to the ground as its foundation is destroyed by the tsunami. Actually, part of the building has been swallowed by the tsunami at the beginning, and it takes just seconds before it's flooded all over. Besides, the buildings in the front block our view of it, so this can do the job. When the building is entirely flooded, there appear some stretched polygons. But it doesn't matter because that is not in view. We only need to make sure what we can see is good. Example here. Take create path geometry because we don't need constraints this time. Here I set the deforming to 1 and the active to 0. So the building will be a passive object in DOP. We set the deforming to 1 so we can apply the building's deforming attributes in DOP and have it inherit the animation we created in SOP. Let's come over to work on the glass. It's also pretty easy. No constraints are needed. So we take create path geometry. Then we deform the glass to match it with the deformed building. Yeah, I want a glass to be active in dynamic solution. Here I match the status of the glass to that of the building, only at the first frame. Then we simulate the dynamics of the glass. These flying points are fractured pieces of the glass. I cache it from frame -15 to frame 80, which basically matches the time period before the tsunami swallows the whole building. And here I add a force in a negative x direction. Besides, I add a box and only allow the glass pieces inside of it to be affected by the force. Of course, you can shatter the glass in the way which you think is best. So that's how I deal with the background building. Not perfect, but simpler. Over here is another building in the background. I used the same method. But if we're working on some standard buildings with elements that can be easily divided, it's best to follow the normal workflow for destruction. The way I introduced just now is only a shortcut to shatter background objects. As to the other buildings in the background, we can destroy them according to our scene setting. Well, let's isolate them. Add a box and delete the buildings on the left. Then add some more boxes to isolate the buildings in need of editing. The second part of this split node outputs the non-selected buildings. They are too far to be seen clearly, so it's unnecessary to deal with them. Here are the buildings we need to work on. This building has almost been swallowed by the tsunami at the beginning, so I only add a transform to animate it, making it lean backward and slowly sink into the water. This animation will do for this case. Alright, let's get down to the other two buildings. From here, we get into the geo to destroy this building. We can directly copy the setups of destruction we created before, modify some parameters, and adjust their animations. Pretty easy. These two buildings are far in the background, so there's no need to put much effort into them. After finishing that, we bring them in here. You can see the animation here simulates the buildings leaning backward as the tsunami ruins their foundation. Merge these buildings together and merge these ones as well. Import them here. So here we have all the buildings on the right, merge them. We're done with the destruction of all buildings on the right. Let's get down to the left ones. Have a look at their structures. Most of them are not standard, so it's not easy to shatter them in the normal way. I take a simple approach. When we simulate the splashes from the collision between these buildings and the tsunami, these buildings will serve as collision objects. But a tricky problem is that some models here are not closed. So let's first solve this problem. I create a few simple models according to the shape of these buildings and merge them with the non-closed models. The problem should be gone. We can use a VDB from Polygon to check it. As shown here, there is something wrong, and they cannot serve as collision objects. But after they are merged with the simple models we created just now, everything is good. I leave the back part of the building non-closed because it won't be involved in a collision. I group the newly created models here so that we can delete them easily before the final rendering. After all, they shouldn't be rendered. Next, let's go through the process of breaking the buildings on the left. As in previous cases, point deform is applied here. Create a box over here as a proxy of these buildings and subdivide it. Bring in the tsunami mesh here. When the tsunami hits these buildings at the foundation, they will deform slightly. To obtain that deformation, I use ray to make the box shrink on the surface of the tsunami. I set scale here to 0.5. This group is of no use, delete it. Transfer the deforming animation to the buildings. See, the foundations are deforming as the tsunami hits them. If we keep the default settings of point deform, the deforming comes out weird, just as you can see here. To fix this problem, we need to make some slight adjustments. Let's come down here, create a group for this background building. I want to make it lean forward when it's hit by the tsunami. So I adjust the translate and rotate. But it goes wrong, obviously. That's because this building is a packed object now. We need to unpack it and make it a polygon. Here, for each is applied for a faster operation. Then add a clean node. By default, it can clean up the unused points. Then cache one frame. Okay, the deformation looks good now. As to the transform node, I just make settings to translate and rotate. Because it takes time to keyframe these parameters. Instead, I drop a blend shapes node to blend between the two inputs. Right here, I insert a keyframe and then insert the other one here. So now the building transforms from this status to tilting forward like this, to match the building's movements with that of the tsunami. Also, make sure that the transition comes out good in the camera view. Next, we come to another building. Group the upper part of it, and then rotate and translate it. Here I use soft transform, which allows us to adjust the soft radius and thus achieve a natural transition. The lower part of the building has been swallowed by the tsunami, and that's why we focus on animating the upper part of it. As to the abnormal deformation here, we can leave it as it is because we cannot see it in the camera view. Hop into camera view to take a look. We can barely see the background buildings. I adjust these parameters for a static tilt status, as I did, and add a blend shapes node here to create the animation of the building when the tsunami hits it. Then we do the same for the other building. Group the upper part of it, rotate, and translate it to make it tilt forward. Also, in blend shapes here, make the building's animation according to the time when the tsunami hits it, and then delete unused groups. Now let's cache it to see how the movements of the buildings come out. So that's what the destruction of all the buildings looks like. I made the flipper with the white water in the foreground. I left out some details in the background because there are too many things and it would take a very long time to make a flipper with them. Here I mainly want to show you the destruction of the buildings. Although we destroyed the buildings on the left in a pretty simple way, viewed overall it's not bad. So here's an important tip. When we're creating a scene with many elements, we need to pay more attention to the overall effect because that decides the priorities of the project, how many details we need, and the time to be allocated for each part. Suppose you're assigned to make the FX for a given scene, and you only have some simple concepts and reference images from your supervisor. Do not struggle with the details of just one element at the beginning, but instead focus a bit more on the whole project. Create the elements that can bring a stunning visual effect first to express what you want. As for unimportant elements, you may not need to put too much effort into them, but you have to create enough details to have them play their roles so that they can help the primary elements to stand out and somehow improve the overall effects. This way your first edition of the project will be more complete and fulfilling, and your efficiency will improve. Then you will have more time to refine the details on the basis of your first edition. So far, we've finished the part of destroying buildings. Catch you next time.